Greetings, everyone. Time to talk about Green's theorem. Green's theorem is a very mechanical side to our integrals that we've been performing. And what it's basically going to do is give us a better way, a more efficient way to perform a lot of our line integrals. And every now and then help us out a little bit with our double integrals as well. Okay, so let's start out with a generic just chat about some mathematical rearrangement that we can do. And this is by no means a full proof, but it should give you the idea of where we're getting the pieces of Green's theorem from here. Okay, so imagine I have some double integral over a region in a plane, right? Just like we did back in the last chapter. Except the double integral, instead of just a plain ordinary function, has the partial derivative with respect to y of this function. Okay, I can rewrite this double integral as an iterated integral where the y integration is between two functions of x. Okay, and I'm calling them r1 and r2. So where I'm getting those from is I'm imagining taking the double integral over some closed region in space, right? Or in the plane, really. And R2 is going to be the parameterization, y equals R2 of x. And C1 is just y equals R1 of x, right? So I just have two functions, basically, in the xy plane, okay? And you'll notice the way the integration is, right? It's top minus bottom, right? Top minus bottom when I'm doing the integrations there, okay? By the fundamental theorem of calculus, though, this integral of this derivative, like so, right, is just going to give me the function evaluated at the top and bottom values, right? So I'm basically putting in R2 and R1 here, and it's dx still, okay? Well, the way that the curves are oriented, though, right, for our normal orientation of a region, you got to remember that everything is right-hand ruled, right? So with my right hand, I want to be able to go around my curves this way, okay, with my normal coming out at me. That means I'm orienting my curves always with the region on the left. So my curves are oriented this way. Okay, now why is that important? Because if you look at these really closely, you should notice that what this really is a function that's been parameterized with x and a function of x, right? So it's a parametric equation, basically. Same thing here, x and a function of x, okay? But the way that the curves are oriented, the curve number 1 should be flowing from A to B, right? So curve number 1 should be flowing from A to B. I kept the negative on that one, right? But curve 2 should be flowing from B to A. Well, so that means I've got to reverse the orientation of the integral, which pops out another negative. Okay, but then look really carefully at this. It's just a parameterized line integral, right? Dx, though. So it doesn't have quite the same meaning as the original ds line integrals, but it's still a line integral. It's still a path integral, path C2 of this function, right? Dx. And then very similarly here, right? I can factor out the negatives, and C2 plus C1 is the entire curve around the region C. So what I have is a closed integral. Don't forget the little circle in there means it's a closed path integration. And of course it's a normal orientation. It's the right-handed rule. You can see the arrow going this way around the curve of this function dx. Okay? Now imagine the same kind of process, but put a dx here instead of a dy, and then reverse your universe here, reverse your x's and y integrations, and then just notice that if I'm doing the y values here from top to bottom, I actually don't have to do this reversal on this guy right here, because the curve number 2 is going to flow this way from the top to the bottom like it should, and then the curve, the second, the underneath one, right, is going to flow from bottom to top this way on the y-axis. And then the y area, when I do the integration, is this way, right? So this is the top, and this is the bottom according to the y integral, this way, right? So if I do this same process but have a partial with x here, then what I'll end up with is a positive and a dy instead, right? So everything's identical, it's just that I don't have to reverse it in the other one, and I would get dy here because I started with partial of x there. If you put both of those together, now and just recap, like put this and the opposite of it together, what you get is Green's theorem. If I take a area integral, a double integral of these partial derivatized functions of x and y, then I can basically rewrite them into this path integral, this curve integral, line integral, around a closed curve of these multiplied quantities. P is the dy, but it's with the x here, right? Q dy is with the partial of x there, okay? And here are the stipulations. C has to be the boundary of R, that's the symbol for boundary of the region R, right? So the curve here has to be the boundary of this region. And this region needs to be simply connected, because the argument that we've used here is just for a simply connected and not really very wavy, okay? If you want to step away from simply connected, then what we typically do is we'll start connecting separate curves inside of our regions to make several simply connected regions, okay? So if you have a more complicated region, we end up just splitting it up into simple pieces and doing several pieces instead. And it ends up having the same properties, but you just have to, do it in pieces. But here's Green's theorem. This is Green's theorem right here, okay? There are some other forms of it, though. You should recognize this format right here, okay? That's the line integrals that we've been doing for a couple of sections now, where P and Q are the components of the vector field that you're integrating in your path inside of, right? So that's why another version of this portion of it right here is the same thing as those path integrals that we've been doing, where it's f dot t or f dot dr, right? Those are the same thing. The TDS and the dr are the same thing, okay? So this side is the same as those. And then you should also recognize this. You've seen it in a couple of different places by now. Firstly, this was the two pieces that you had to find to see if a vector field was conservative, right? The second component, partial x, would have to equal the first component, partial y, for a vector field to be conservative, okay? Also, you would have seen this component when we were performing the curl in a 3D space. This would have been the z component of the curl in that space. So one way or the other, no matter which way you look at it, this is going to end up being something involving the conservativeness of your original vector field PQ, right? Okay, well, that's where this piece comes from. The curl dot K. In other words, just the K component, right, of the curl. And that's what that is. But when you rewrite Green's theorem with these dot products of vector fields and curls of vector fields in this other format, it actually becomes something a little bit more generic called Stokes' theorem. And Stokes' theorem can actually even be generalized to higher dimensions beyond this as well. Okay, so this is an alternate form of Green's theorem where we'll be doing a lot of work with vector fields. Okay, not so much in this section, but definitely in the future. Another alternative of this is, if you remember, if a vector field was conservative, then any path integral through the vector field was 0. Well, as we were just saying, if the vector field is conservative, these two quantities are equal, and you're going to get 0 from the subtraction. So the alternative form is the path integral, right? PQ is f, dx dy is dr, right? Closed integral, f dot dr is 0. That comes when f is conservative and the path is closed. We called that in the last section path independence. So it also is built into this as well, right? Okay, and then lastly, a huge twist around that we'll definitely talk more as the next few sections come up, and we start doing like surface integrals and the big triple integrals involved with surface integrals and things like that. Okay, that goes along with a more generic version of this alternate form, but here's what it is. Notice that these path integrals are the normal f dotted with the tangent vector, right? Tangent vector's here on a curve, right here. If you also would prefer to do f dotted with a normal vector, and notice I'm using little n instead of big N. Big N always points towards the curvature. The little n that I'm talking about is pointing in the opposite direction. So it's not that primary normal vector that we're talking about. This is the normal to the surface, a lot of times is what it ends up being. If this were some sort of surface coming out, the n would be normal to an entire surface. But here it's just to a curve, okay? But sometimes that's an important dot product, just like the f dot t. F dotted with the tangent vector is something that's involving the motion of something, right? Or the work or the energy involved with motion, okay? Whereas f dotted with n tends to be more like what we call flux. Something passing through something else, like if I have some barrier, how much of a vector field is going through it, that sort of thing. Well, that's why it's dotted with n, right? The normal vector, how much of the field is in that perpendicular direction. So that's also an important path integral that needs to be done, right? Dotted with ds because it's along a curve and later on across an entire surface, right? So how is this the same thing as Green's theorem? Well, the n ends up being perpendicular to the tangent vector. And remember, in 2D, to do perpendicular, all I need to do is reverse components and change a sign, right? So if you end up reversing components here and changing a sign, notice that what happens is your derivatives also reverse and you get a plus. And so really what that is it gives you a divergence, because you'll have dp dx plus dq dy. And remember, it's p and q in your field, right? So that's just the divergence of your field, okay? So this is just another alternative form that has to do with the normal vector instead. And the fact that it's perpendicular is why the components can switch and the sign changes to a plus, which gives you the divergence there, okay? But for now, mostly in this section, we'll be dealing with this Green's theorem, okay? So let's get some examples. I want to start these first two examples out as things that you know and love from previous lectures. These are both vector fields that we've been dealing with on several different occasions, and I've done the line integrals several different ways. And I'm here to finally go ahead and put the nail in the coffin this last time, and we're going to hit these fields again, and you're going to see how we can get through these things efficiently with Green's theorem, right? Of course, it needs to be a closed path for Green's theorem to even be considered, right? So I have my vector field, y negative x, and I'm interested in doing the path integral of f dot dr along a c that's closed, right? So here we are. This is my path c. I've split it into two pieces, c1 and c2. And the first piece is the leg of the line y equals x from the point 1, 1 straight down to 0, 0. Then the second leg is going to be y equals x squared from 0, 0 back up to 1, 1. So it's a closed path, okay? F dot dr ends up being y dx plus negative x dy. This is a simple region. There's no singularities of any kind. It's completely continuous in there and everything, right? I've got it's all closed and simple. So that means for Green's theorem here, I can convert this into a double integral over the region in question of the partial x derivative of the second component minus the partial y derivative of the first component, like so, dA. Well, the partial of x is negative 1. Partial of y with y is 1. So I've got negative 1 minus 1 right here. So that ends up being the double integral over the region in question times negative 2 dA, or of negative 2 dA. Well, now we're back into last chapter. I'm just doing a double integral now. I'm going to convert it into an iterated integral for my region now. Right? Okay. So here I go. I'm going to pull the negative 2 out, make it easy on myself, like so. Right? And that's just going to leave me with dy dx. Okay. Well, and I did dy first because I've already got my curves here set up for y equals. So we're going to do top minus bottom, right? The line is on top, the x squared is on bottom. So that's going to be from x squared to x. And then x just goes this way, right? From 0 to 1. So 0 to 1. Iterated integrals, right? So then I've got negative 2, integral from 0 to 1. The integral dy is just y, top minus bottom, gives me x minus x squared dx. Okay, so I've got negative 2 times 1/2 x squared minus 1/3 x cubed, evaluated from 0 to 1. Plug in 0 is gone. Plug in 1, and I've got 1/2 minus 1/3. Like so. But that's just 1/6, right? Because that'll end up being 3/6 minus 2/6. So I've got negative 2 times 1/6, which ends up being negative 1/3. Now, if you recall from the last lecture, we actually got that 1/3 value the last time, but we were going in the other direction around the solid, right? So this time we have a negative 1/3 because we actually took on the normal orientation, what we call the positive orientation, or the traditional orientation with the right-handed rule, and the region would always be on the left of your arrows. Okay, so we got the negative 1/3 this time. Other example. There's our B field that we seem to see a lot of lately, y over x and negative x squared. The last time we actually did both of these line integrals already. I used the path xy equals 6, right? I'm calling it gamma 1. And x plus 2y equals 8, the straight line path, I'm calling gamma 2. We did both of those line integrals separately, right? We did the actual gamma 1, which was from 2,3 down to 6,1, and we got 26 for it. Okay, we did it the long way. We parameterized it and everything for that one. I did it a couple of times. Then this one, we actually did the opposite orientation because we weren't putting the paths together last time. I just did 2 separate paths to show that they were different values. But notice I have the negative on gamma 2 here. That's because this is the integral that we did last time, and what we did was we actually went from 2,3 to 6,1 also along that line, which is the opposite orientation than what I have labeled here. So the opposite orientation of what I have labeled gives us this value. Okay, so if you flip it around, what that negative actually does is it just changes all of these to negatives. Okay, and then you're just going to do 26 minus this if you're going to end up adding up the whole thing piece by piece by just doing the curve integrals, the path integrals, right? The line integrals. If you want to do the line integrals piece by piece, do it. Great, fine. Green's theorem offers us an alternative, right? I'm just going to take the entire path gamma. It's a closed path, right? Simple region. It's all connected and everything. So b dot dr is this path integral, this line integral, y over x dx, negative x squared dy. Since it's over a closed path, simple region, Green's theorem says that this is equivalent to the double integral over the region in question, this region, right, of the partial with respect to x, negative x squared, minus the partial with respect to y of y over x, and then that whole thing with a dA, area element, okay? So then what is that going to be? Let's go ahead and set up the whole thing. The iterated integral, right? So I'll split up my integrals here. And again, I've got my stuff set up like I would like to put it into y, right? Okay. So then for the bottom curve here, right? I'm integrating this way, like I'm doing the dy then the dx. So from the bottom, that's 6 over x. To the top, that's going to be 4 minus 1/2 x. Right? That's this to this. All right. And then the y values are doing that. The x values from left to right are going from 2 to 6. From 2 to 6. Okay. Partial with respect to x of negative x squared. That's negative 2x. Minus partial with respect to y. That's just minus 1 over x. And then I did dy dx like that. Okay. Notice there's no y's here, right? So really I'm going to take this parentheses and just pull it out. Integral dy is just y, top minus bottom. So I'll jump a little bit here. 2 to 6 times 4 minus 1/2 x minus 6 over x, like that, dx. That's top, this thing, minus the bottom, that thing, right? This was antiderivative of dy, which is just y, right? Top y minus bottom y. Okay. So I can, multiply that out, make it a little bit easier on myself there. From 2 to 6, I have negative 8x, and I have plus x squared, right, from here to here. And then I've got plus 12. And then I've got minus 4 over x, right? Okay, then I've got plus a half, and then plus 6 over x squared dx. Any crossovers? Yeah, right here. The 1/2 and the 12 I can combine to be 25 over 2, right? So plus 6 over x squared dx, like that. Okay. So let's see. Antiderivative, I've got negative 4x squared plus 1/3 x cubed plus 25 over 2x minus 4 ln, absolute value of x, but we got nothing but positive values. And then minus 6 over x there, right? All right. That's evaluated from 2 to 6. Okay. So let's plug in the 6, right? So I've plugged in the 6 and the 2, and basically I just did individual subtractions, right? 36 minus 4 is 32 times the negative 4. 216 minus 8 is the 208, so on and so on. I just did all the individual subtractions in each step. And you'll notice when you combine this, you get the negative 20 over 3 minus 4 ln 3, which is exactly what you get when you subtract 26 minus 98 thirds plus 4 ln 3. Okay? So the point was, you can do the path integrals separate when you make your little paths, but if they form a closed region and all of your pathway is the boundary of the entire region, then you have Green's theorem that can consolidate it into a single integral. Okay? Sometimes one's more work than the other. It just depends on the integral. Okay? So now let's look at a couple of examples that you wouldn't even want to do any other way but Green's theorem. Green's theorem is going to allow us to simplify these things immensely, to the point that they're even palatable and doable, quickly, versus possibly not at all. Okay? So first example, perform this path integral, right, on a closed path C, such that C is the circle x squared plus y squared equals 4, moving clockwise, right? So be sure that you draw these things out either in your mind or on your paper, right? So what we have here is something with a radius of 2, right? Centered at the origin, but it says clockwise, which means that it wants us to orient our integral, our path integral, right? Because that's what we're actually doing here, is a path integral. It wants us to orient it this way. And notice the right-hand rule, my thumb's pointing in, right? And if you look at your arrows, the region that you're integrating inside of is on the right instead of the left, okay? That's the opposite orientation. So for our C right here, the Green's theorem is not going to apply unless I reverse the direction, right? So what I'm actually going to do is say that it's the negative of the integral, the double integral over the region of the partial with respect to x of 3x plus 2xy minus the partial with respect to y of y squared plus x, and then dA. Okay? Again, the negative was because of the way the orientation of my path integral. If you were to actually set up this path integral, okay, and just work it out like it is, you're going to have that negative built in there somewhere because of the way the flow of the path is going, okay? Instead, I'm using Green's theorem, and the region itself, the region is not oriented. I have to make sure that I'm paying attention to my curve orientation in order to do the correct sign on my integral here. Okay, so let's see, let's simplify. I've got my double integral over r. Partial derivative here with respect to x is 3 plus 2x. And then partial with respect to y of this guy right here, I've got, whoops, not 2x, 2y, David, minus 2y, dA. Well, this is nice, right? Plus 2y minus 2y, I just get 3 dA. 3, whoops, forgot my negative. Double integral over the region dA. And don't forget, a double integral over a region dA is just the area of the region. If you already know how to do the area of the region, you got it made. So it's negative 3 times the area of my region. My region is just a circle with radius 2, right? So this is just going to be negative 3 times pi r squared. Altogether, negative 12 pi, right? Now remember what we were doing here. We're actually calculating a path integral. So if I were to walk along the curve, right, and integrate these pieces all along the way, just whatever it happens to be, this is the result of that path integral, okay? Another example. Oh, well, actually, wait. Before we move on to that, try and do this one with the path integral, right? That was the whole point, actually, also, was the fact that if you try to do this, the path integral the long way, right? First of all, I'd have to parameterize this thing nicely because it's a closed curve. If you don't parameterize it, you'd have to split it into two curves and do the two separate curves. Either way, that's going to be a mess and a half. But if you parameterize this, say, x equals 2 cosine t, y equals 2 sine t, and plug in all those trig functions. Dx would also be an extra trig function, multiplication. You're having a pretty extreme mess of sines and cosines in there. That's really hard to get out of that convolution, okay? So I hope you can see how much simpler this process was. Now, this other one. Most of the time, even to set up the dot n in these pathway integrals is a headache, okay? I have to parameterize the region. I then have to do derivatives and second derivatives and cross products, and I have to find the normal, right? Then I have to plug it in here with a dot and still with the ds. It's a mess, right? Green's theorem, however, in its alternate form, right, a watered down version of the divergence theorem, showed us that I can do this as long as it's a simple region on a closed curve, right? Well, okay, let's look at it real quick. All it says was the region is in between x squared plus y equals 4 and the x-axis. All I have to do is define my curve C to be C1 plus C2 here, where C1 is the axis flowing in this direction, and C2 is my other curve flowing in that direction, right? That's my region going this way, and then I've got this region on the inside. Okay, so then this thing becomes the double integral over my region of the divergence of my W, right? Divergence is when I do the dx of the x portion and the dy of the y portion, right? Don't forget the dot product here. What I'm doing for this piece right here is partial of W1 with respect to x and partial of W2 with respect to y, right? Recap on that back in a couple of sections ago, doing the divergence on a vector field, okay? So in this case, I'll be doing the x derivative of y cubed, which is 0. And I'll be doing the y derivative of yx, which is just x, dA. Okay? So then that's equal to, we can go ahead and do the actual integrals here, right? I'm going to have x, and then let's go ahead and do dy dx. To integrate the region in the y direction, I'm just going to go from 0 to 4 minus x squared for my dy. And then x just goes from -2 to 2. So right here, the x, of course, can get factored out to here. I integrate dy is just y, so it's top minus bottom. I get -2 to 2, x times 4 minus x squared dx. And I'm going to cut a shortcut here. I'm noticing that this is an odd function over symmetric limits, right? Multiplied in, that's 4x, and x cubed, that's an odd function. Symmetric limits of any odd function is going to be 0, right? So again, think about how much work it would have been to do the path integral itself here versus using the Green's theorem to work it as a area of a region instead, okay? That's really the upshot here. This is what Green's theorem is doing for us, allowing us to really reduce our mechanical time behind these integrals. Of course, you can also use Green's theorem in reverse. If there's an area integral, a double integral of some sort that you find more difficult, you can always revert it back to a path integral. A huge example of this that's even used in certain machines is how you can find the area of a simple region just by tracing its boundary. Okay? Because of Green's theorem, we have a way of just path integrating around the boundary of a simple region, and it will give you the area of the region, right? The only stipulation is that your two components of your vector field, P and Q, have to resolve this equation right here. The partial derivative of Q with respect to X minus the partial of P with respect to Y, that's that portion of Green's theorem, has to equal 1. So that you're doing 1 times dA and you're doing the area of just the region. Okay, well, a few simple results of that is letting P be negative 1/2 Y and Q equal 1/2 X. When that's true, you get this formula for the area, just tracing around a curve, closed curve. Or if you let P just be negative Y and Q be 0, right? If P is negative Y, right, you get negative 1, negative 1, will give you 1. Then you get this result from plugging it into Green's theorem here. Or letting P be 0 and Q be X. You can get this result, right? You get X dy and 0 dx. You'd have this version of the area formula. Okay? It just depends on the situation as to which one will flow the best for you. Let me show you a couple of examples. Right here, I have the area between the curves y equals x squared plus 2 and y equals 5x minus 4, right? Okay. I'm going to use the integral of x dy on a closed path. Okay, let's make sure that's exactly what I have, right? As long as I orient my curve correctly, right? It's this way, and then back this way. It's going this way around. I just need the intersection points then, up here and up here, right? I need to just find those two intersection points. And the same thing over here. Okay? Easy to find those though. You just set these two equal to each other. You'll notice that you, let's see, get your simple x minus 2, x minus 3. So you get 2 and 3 as your two intersections, right? Of course, good old algebra. All right, but this is a path integral, and it's not just one solid path, is it? I've got two separate curves there. So I've actually got to split this into C1 and C2. But they're both x dy. It'll just be a different x and dy in each curve, right? So let's label them. We'll call this bottom one curve 1 and the top one curve 2 there. For curve 1, x is just x. dy, though, in curve 1, that's the parabola. This is curve 1 right here. Right? That's C1. This is C2. What is dy? If I do the derivative of y, do I not get 2x dx? Like that. Okay? And then that's got to be evaluated from 2 to 3. Plus the second curve, right? Be careful now, the orientation of the second curve is such that I'm evaluating from 3 to 2, right? Watch your orientation on your curve there. For the second curve, my y is equal to 5x. So I have x times dy is just 5 dx, like so. Okay, so I can make this a little bit easier on myself just by making it one integral from 2 to 3. And all I need to do that is reverse the direction on this, right? So that's just 2x squared minus 5x dx on the whole thing, right? So then I can just do that integral. That's going to give me 2/3 x cubed minus 5 over 2x squared, evaluated from 2 to 3, right? But then that's just going to give me 18 minus 45 over 2 minus 8/16 over 3 plus, because of the double negative, 10, right? Let's split this off here. We can get a final result on our area there. Ends up being 1/6. And of course I know from Calc 1 we have already done, you can do the area between two curves, top minus bottom, integrate from beginning to end, sure. Debatable, could be about the same amount of work, right? It's pretty close. But then what about this next one? Area under a cycloid, right? A cycloid is this shape that basically follows a point on the top of a wheel as it rolls around like this, right? That can only be done parametrically. The parametric equations for this cycloid, we'll just do a simple one, size 1. Okay, got this, like that. That's for the curve up top. Now don't forget, I have to have a closed path to do this integral, right? So the bottom path right here is the x-axis. The top path is that curve right there. So the bottom path right here, I'm just going to parameterize. The bottom path right here, I'll call it C1. This other path right here, I'll call C2. C1 being the x-axis is just going to be x equals t, y equals 0, right? Okay, so I'm going to split this into the two curve pieces here. I'm going to have negative, because of the whole negative here, integral of C1, y dx. Well, y is 0 on C1, and dx is just dt. Well, that's nice. Integral zeroes out, right? Minus, and then I've got my second integral there for curve 2. Integral on curve 2, y and dx. Y is 1 minus cosine t. Dx is also 1 minus cosine t. So it'll be squared dt. 1 minus cosine t is my y, and dx is also 1 minus cosine squared. Just repeat it real quick. So it's 1 minus cosine t squared dt, right? This one is 0. That's nice. And I'm just doing this integral here. Okay, so on my pathway, I need to notice that this point right here, right, when it actually hits the ground again, is at pi, right? Because I'll have pi minus 0. Oh, I'm sorry, at 2 pi, because what I need is for it to hit the ground again. So it's 1 minus 1 at 2 pi. But I'm going in reverse on curve 2. See curve 2 on the top right here? It's going in reverse. So I need to go from 2 pi to 0. But I had the negative carryover. And then I'm foiling this out. Of course, the cosine squared t right there, I'm going to evaluate as the power reduction, cosine 2t dt. Okay. And I'm going to shortcut it again. I hope you remember your trig, but from 0 to 2 pi of cosine is a full cycle all the way above and all the way below, right? So this piece is going to go to 0 because it's all going to add out. Same thing here with the cosine 2t. If I integrate this piece from 0 to 2 pi, a full cycle, in fact for that one it's a full 2 cycles, right? That piece is also going to go to 0 when I'm integrating that. So what I'm left with is 1 plus a half, which is 3 halves, dt. And this negative is going to allow me to flip the integration here. Okay, so what I've got is 3 halves integral 0 to 2 pi dt, which is going to result in 3 pi. Okay? So sometimes Green's theorem helps us go in reverse. I can turn an area integral back into a path integral when it becomes necessary. So one last example here. What happens when you don't have a simply connected region? Okay, so here's one way that can happen. What if I've got like some sort of, it's not quite an annulus, right? Because the outside's an ellipse here, right? I have the region between this ellipse and this circle here. And I want to find, say, the work being done on just this region or something like that. Okay? And I've got some vector field and it's acting in this region, but I don't want the interior region. So what I've actually got are two separate curves there. It's not a simply connected region anymore because the curves that make the boundary are not connected. Okay? So it's not simply connected anymore. I can't just jump straight to Green's theorem of just this piece. Okay? So here's what happens. I have to find a way to make it one connected piece. Since I wasn't given any orientations for these curves yet, that's to my advantage. If you're already given orientations, then you may have to play around with some negative signs. Like if you go against the flow of one of the curves that you've been given, then you'll have to switch the sign on something or something like that. Okay? So here we go. Basically what I'm going to do is I'm just going to connect these two curves just like this. Okay? So let's do normal orientation. C2 should flow this way, right? C2 should flow this way on the outer edge. That's my right-hand rule, and look, it's to the left, right? The region is to the left there. Okay, but then let's take a little detour, right? As I'm going around C2 here, I'm going to hit this juncture, and I'm going to travel this way momentarily. Okay? And if you want to call that C3, you can. Okay? Then when I do that, I'm going to want to travel with the flow of what I was doing. What does that mean? The area needs to be on my left. So turn your head upside down. You'll notice on the left means I would have to rotate this way. This way. All the way back around until I hit that juncture again, and then I would travel back across to C4, right? Across C4 back to C2 here. And then notice the flow of that is all connected up. Okay? So let's go through it again. I'm going around this way. I'm hitting the juncture, going around this way, hitting it again, coming back and continuing. So it'll keep going around like that. Okay? And what I've done is I've made a completely contained region with my curves there. And if I have to, I can actually split it into separate simple curves, okay? Or even better, if you don't like the way the one piece is doing, you can actually split it in a couple of places. Like I could split it over here too if I had to, okay? But here's the good news. It's the same pathway on these two connectors, right? So the path integral on C3 plus the path integral on C4 are going to be exact opposites because it's the exact same path, but they're being traversed in opposite directions. So essentially, those two integrals are going to wipe out immediately, and I don't even need to worry about them here, right? Okay, so then what's going to happen is I'm just going to have this closed path integral. Now that I've got it all closed in, I can set it up. Okay? Since I was able to connect it up, I didn't have to worry about my orientations or anything like that. I'm just going to do f dot dr here. So I've got 5x4y plus 2 dx plus x to the 5th plus 7x dy. Okay, I've got it joined between two simply connected regions. The orientations are basically handling these things for me. What's going to happen is I'm going to end up doing the double integral over the region, right? This region. And you could look at this a couple of different ways. You could say I'm doing the path integral of just this one, and then the path integral of just this one. And since this is the opposite orientation, it's going to get subtracted, right? Because this is technically going the other way. If you include the inside piece with it, right? Then technically this is a negatively oriented curve, okay? That's one way of looking at it. I'm just going to look at it like this. The region, now that I have all of my stuff simply connected like it's supposed to be, the region is this, okay? And I'm going to do my Green's theorem here. So that's the partial with x of x to the 5th plus 7x minus the partial of y, 5x to the 4y plus 2, like that, dA. Of course, I can do the partial of x here. That's just going to give me 5x to the 4 plus 7 minus the partial of y here is going to give me 5x to the 4 and 0. 5x to the 4 minus 5x to the 4. It's still over the region. It's still dA. But now I've just got 7. So I have 7 times the double integral over the region dA. Now again, there's a couple of ways you could look at this. I could have split this into two path integrals, okay? Because they are both completely closed paths. C2 in and of itself is a closed path. C1 is a closed path with the opposite orientation. I could have done integral minus integral. I saved myself a little bit of space here, and I'm just saying, okay, well, it's all connected anyway, and I'm going to do the double integral over the region entailed, which is the in-between, right? Since it's just a region that I already know how to do the areas of, it becomes a subtraction. Now, let me state, sometimes you may want to actually separate these out and show all of the steps with the different path integrals of these curves here. This one's a pretty straightforward one, and the areas were pretty straightforward. Okay, just to show you how we can actually justify doing it is really what this is. Okay, so I have 7 times, and then I just need to do the area of the ellipse minus the area of the circle. So the area of ellipse is pi times A times B. My A is 5, my B is 4 on the ellipse, right? A is 5, B is 4, minus pi times the radius squared, right? My radius here is 2. So I have 20 pi minus 4 pi is 16 pi. Which gives me 112 pi. Okay? Recap. Again, what did we do? We calculated a path integral, but it's two paths, right? What I've really done here is I've figured out how to get all of these path integrals inside of this vector field added up together in an efficient way. Green's theorem has enabled me to recalibrate, to rewrite this in a much more efficient way. Because it is a closed path, because I was able to make it one connected region by using my little cheat here of these two. If that's not strong enough, you can always connect it in a couple of places or several places. Eventually what you'll find is that all of those connectors add out in their integrals, right? Because this is a straightforward way of connecting it. If you have two regions that are physically separate, you can do the same thing, connect them with a pathway and try to make it one continuous thing like that. Most of the time, there's a way to make these things work, okay? All right, so I hope this has helped you understand Green's theorem, and then that helps you perform your integrals more efficiently.